Well, first of all, I would like to thank Professor Quark for his invitation and for arranging this talk for me. Thank you for your hospitality. And, well, my talk is about, generally about actions of the group about actions of n-dimensional additive group. Well, I hope to come to my part of it, which is devoted to automorphisms of the quadric, which are associated with actions of this group. But now the first subject is the simplest action of this group, linear representation. Let us have some linear representation of group in n+1 dimensional complex space. We will consider the representations which are non-degenerate in some sense. I mean that the space of representation should contain a vector v such that linear span of its orbit coincides with the whole space. There is a method.
GV is the orbit.
The linear span of the orbit is the whole space.
G.
G is the group. G A N. Well, there is a method to study such a representation. It was described by Brandon Hassett and Hassett-Tschinkel. In 1999. Its idea is that they state some correspondence between such representations and zero-dimensional subschemes in CN. To be more precise, I will, of course, formulate their theorem. There is a one-to-one correspondence. Between the following. First, isomorphism classes of pairs rho v, where rho is such a representation effective rational and with a cyclic vector.
The representation is given.
No.
No?
No, we consider different representations. It is not given. There is a one-to-one correspondence between isomorphism classes of all such pairs with, I don't know, any rho and any cyclic v.
And if we span the whole space?
Sorry?
Any v such that...
Any v is cyclic, yes, such that.
Any v.
And but n is fixed or?
Well, for in for each pair rho v, there is a fixed n and m. And when I write the second point, there will be some classes of pairs u, and it will be possible to count n and m for them, for each of them. And of course they correspond. Значит, isomorphism classes of pairs RU where R is a local algebra supported at the origin and of dimension m plus 1. And U is a local algebra means that it has a unique maximal ideal M. And U is a subspace in M such that dim U is N and U generates the algebra R. In other words, it means that R is a factor algebra. It's a finite dimensional factor algebra and supported at the origin again. And U is just the linear span of the images of the generators. Well, it means exactly that the spectra of this algebra R is just some zero-dimensional subscheme in Cn supported at the origin again.
What is pi? Pi?
Sorry?
Pi? Pi.
Question back.
Pi is the quotient map
Yes.
from
This polynomial algebra to R.
yeah, you're right. So U is equal to this one?
U is equal to to the linear span of so it is of dimension n in general case, and it generates the algebra R as is written here. Well, the idea of this correspondence is such that if we have a pair rho v, we just
What is the meaning of the dimension U?
Well, U is some linear subspace of M. It has a dimension.
That means vector space to me.
Yes, vector space
Okay.
with a dimension. Well, here it is written. It is a linear span of some things. Okay, the idea is that if we have the pair of V, then we obtain the algebra R by introducing the structure of algebra just in the space Cm plus 1. There is a, I don't know, it can be explained for a long time, but the general idea is that we take the space of representation and introduce the structure of algebra using the representation rho. And V will become a unit in this algebra.
So in this case,
Yes?
n is equal m plus 1?
No.
No?
It is, no, of course not. Well, we have some, I don't know, we have some polynomial algebra and we factorize it in any sense, but we should get finite dimensional something, finite dimensional factor algebra. It can be of any dimension. Well, then it is shown that R is a factor algebra and U is just, again, the linear span of the generators. Conversely, if we have first an algebra R, written as a factor algebra, then we can construct the representation rho where n is the dimension of U and n plus 1 is the dimension of exactly like this. In this way, to n complex numbers, which are some element of the group, we associate the operator of left multiplication by the exponent of a1 x1 plus so on an xn. In this case, we have, well, since the algebra R is supported at the origin, it means that any generator x eta in some power k eta, k is, is 0 in R, which means that the exponent, if it is written as a row, is well defined. So there is a finite number of summands. Well, and for the marked cyclic vector, we take the unitary element in R. So we have more or less described the correspondence stated by Hassett-Tschinkel. And yes, the representation rho is faithful, so it has no kernel if and only if there is no, no linear combination of generators comes into the ideal itself, so there is no, I don't know, extra generators which die after factorization at all. Okay, we call the corresponding algebra. So in this case, if the representation row is... Yeah? Sure.
It's faithful if what?
If and only if, значит, не пересекаются. Сейчас. Zero, yes.
So no linear to zero. How to multiply by just exponential?
Well, we have some algebra which is a factor algebra of polynomial algebra,
Yeah.
and we have an exponent which is, as I said, just some polynomial of x1 and so on xn. So we have two polynomials, and we just multiply one by another.
Sorry.
Yes?
I cannot understand the correspondence. So in our case, rho and v is given, right?
Here rho and v is given, and to get rho r, we introduce the structure of algebra, and it is ended here.
Could you tell me how rho defined explicitly in the case?
In this,
Yeah.
I don't know. It is some representation, any representation. No. If we take some pair, then it lets us construct the algebra R, which depends on rho and on v, of course,
Okay.
which is constructed by something. Well, it was the first main theorem, and we have...
R is algebra?
Yes, R is a...
The same vector space. So
Well-
multiplication is how multiplication? Component-wise multiplication. Or
Sorry?
you wrote R equal C.
R equals this as a vector space.
Yeah.
The point is that we have to introduce the structure of algebra in this vector space. I will not explain how exactly, but it depends on rho and v. And this is just the idea of the theorem, that we take the space and introduce a structure of algebra.
So are you going to explain how define the algebra structure on the vector space, or skip over?
I think I will skip. Maybe if I have many time, I can
Okay.
return to this. But I don't. When I read it, I don't know. I think it's mostly technical.
Yeah.
I don't think it will help you anyway. Okay, it was about linear representations. If we proceed to projective representations, we will begin with the simplest case, when m equals to n. First, I would like to note that a faithful representation, linear representation, rho of our group always determines the projective representation which is effective. And the corresponding action of the group GAN on the space PM is Pn, the same, is locally transitive if and only if, no, here is M again, if and only if M equals to N. So we can, so if we look at the case M equals to N, we will get some theorem about not all the representations of some sort, but we will know something about locally transitive action of the group GAN on Pn. Well, also in this case, we know that U is just some subspace in maximal ideal M. But in this case, when M equals to N, we see that U is equal to M. And that, well, there is no need to fix the realization of R. I mean that if we take the algebra R, then in this case U is already determined because it equals to its maximal ideal. So the second theorem of Hassett and Tschinkel again is like this.
You can use also side blackboard.
It's too late.
Yeah,
Thank you for the idea. Okay. There is a one-to-one correspondence. Between the following. Locally transitive action. Actions of the group GAN on space Pn and local algebras supported at the origin of dimension n plus 1. So there is, in this case, there is no more, I don't know, extra. It is much simpler. There is no V because it is more or less determined by the action up to the action itself. It is any vector from the open orbit here. Well, it was one of the simplest. It was the simplest case of projective representations. There is a way how to describe all the actions by just classifying local algebras of some type, or if you like, by classification of zero-dimensional subschemes. So this theorem helped Hassett-Tschinkel just to list all locally transitive actions of this for n less or equal than 4. There is only a finite number of actions for each of such n, and they also showed that if n is more than 4, then for each n there exists an infinite number of locally transitive actions. And here I don't remember, for n equals, for n is 1 there is 1 action, for n is 2 there are 2 actions, for n is 3 there are 4 actions, and for n is 4, I don't know, about 10. So the next question was stated by Hassett-Tschinkel in the same paper in 1999, and it is the question to which my work is devoted.
Can you introduce the paper?
You mean the name? Oh, I can look, but I don't remember. I can look. The paper. Geometry of equivariant compactifications of the group Gn.
Okay, wait.
This one.
Okay, I read.
Okay. Well, they. Так, это что? If we consider the case when m equals m plus 1, just then нет, что-то я ерунду какую-то пишу. Then the closure of the orbit should be some hypersurface in Pn plus 2. And the question was when this hypersurface. Почему plus 1? Ну да, NPN plus 1 точно. Так. When the surface is a quadric. And a non-degenerate quadric. Well, we will again use the first theorem, and then we will use its results in a projective case.
Why quadric is important? The kind of orbit.
It is not very important. It is just the simplest.
Simplest.
Yes, because now I don't know, it is not just a hypersurface of degree 2, but it is also associated with a group. I mean, if this case we can associate with the group SA, then a quadric we can associate with the group SO. And in some, I will use it, this fact that it is associated with an orthogonal group, but in general it seems that I can guess the degree of this hypersurface. It is not in my paper, but it is more or less done by now. Well, the question is when it is a quadric. If we have to find just some pairs, RU, RU, we will we have to find a correspondence between actions of the group GAN on the quadric non-degenerate and some algebras with an additional structure. It was the question as it was stated by Hassett-Tschinkel. And the main result of my work is the third theorem, that for each n there exists a unique, up to isomorphism of course, action of the group GAN on non-degenerate quadric Qn. It corresponds to the algebra R, which is the factor algebra of a polynomial by the following which means that well, all the squares are the same element, and another multiplications give 0. Well, let me sketch a little the proof. First, since the group of automorphisms or the quadric is then we can say that any action of the group GAN on a non-degenerate quadric Qn can be extended to an orthogonal not extended, it induces the orthogonal representation of this group. Then after this extension we can use the first theorem and so if we have some let us have some action on the quadric. Then we can extend it to an orthogonal representation, and then we can construct an algebra R as we did in the first theorem. Then we will use the orthogonality of the representation, and it lets us replace the condition that the orbit closure is a quadric. Instead, we can use something more algebraic and more useful for me, that there exists a bilinear and G invariant form B on the algebra R. So then, using the orthogonality again, we can just write it down. The point is that such form exists if and only if the dimension of the square of maximal ideal in R equals to 1. It is the only case when a form exists and when the action on the quadric can exist at all. And in this case, when the dimension of the square is 1, this form is determined uniquely up to scalar multiplication. It can be written as follows. If the algebra R is a linear span of 1, x1, xn, y, or where x, e is just the image at factorization of the generator number e, and m squared is the linear span of y. In this case, the form is of the following form. So the first and the last vectors are orthogonal to everything another, and between them there is -1, and b of xi xj equals to aij, where x a xj is aij y. Since y is the generator of m square, then any multiplication should be of this form, and so we can define aij. But then we can change the basis in the subspace x1, so on, xn, and we will obtain the form where E is an identity matrix, which means that we can obtain that xi xj equals to delta ij y. But this means exactly that there is we can see that if the square of m is one-dimensional, then the form B and multiplication in the algebra R determine each other. So as we see that the form B is unique up to isomorphism, it means exactly that there is a unique algebra R for each n. So if we get back, we will see that there is a unique action on a non-degenerate quadric. So it was the sketch. And the last remark is that if we consider any local algebra R, of dimension n plus 2, such that the dimension of the square of its maximal ideal is 1, then the closure of the orbit, of the corresponding orbit, will be again a quadric in any case, but it can be degenerate in general. And moreover, degenerate quadric can be closures of orbits for some actions of absolutely different type. So I can give an example of two algebras which are both local, and which of them is of this type and another of absolutely another type, where this closure will be the same quadric. Well, I can write them.
So
I cannot.
the equation. What is the equation?
Sorry?
The orbit, which it is when it is quadric.
What is the quadric if the... Сейчас надо сообразить. Something very easy. Something very, very easy. Very, very easy.
Later,
Well,
maybe. Yeah. After
maybe.
your talk.
Oh, okay, I will write you, of course, but I just can't think now.
Yeah.
Oh, sure. Well, there is a... That's more or less all, and the time is up.
So you are done.
Yes.
This is just theorem 3 is your result, right?
Yes.
Do you have some questions? This is the hard part.
Is there any similar correspondence in the case of multiplicative group?
Well, the case of multiplicative group, it is...
C star and C star and N.
Yes, I see. I think there are many... Another thing. The multiplicative group is much more simple, and I think it can be described without such correspondences. There are many other facts known. I don't know about the exact theorem, but I don't think there is any need in it.
Okay, thank you very much.